is given the next information. This question asks you to explore some properties of polygonal numbers and to determine and prove interesting results involving these numbers. Polygonal number is an integer which can be represented as a series of dots arranged in the shape of a regular polygon. Triangular numbers, square numbers, and pentagonal numbers are examples of polygonal numbers. For example, a triangular number is a number that can be arranged in the shape of an equilateral triangle. The first 5 triangular numbers are 1, 3, 6, 10, and 15. The following table illustrates the first 5 triangular, square, and pentagonal numbers respectively. In each case, the first polygonal number is 1, represented by a single dot, and it is given the next table. Type of polygonal number. The first row it's for triangular numbers and geometric representation. We can see the first number it's just 1 dot. The next number we add 1 dot in a row and complete an equilateral triangle, so it's 3. The next is 3 in a row, and we can see a pattern, and hence values are 1, 3, 6, and so on. Square numbers. You can see a pattern. It's quite easy to understand it. And pentagonal numbers, values 1, 5, 12, and so on. And it is also given that for an r-sided regular polygon where r is positive integer, r is greater or equal than 3, the nth polygonal number PR of n is given by this formula, where n is positive integer. And hence, for example, for square numbers, P4, it's because square numbers, it means r is 4, and it's number of a number. For example, 6, it's a number with number 3. And you can see if we simplify it, we get that it's n squared, and we can check when n is 1, the first number is 1. When n is 2, the second is 4. When n is 3, the third is 9, and so on. And questions. AI 2 marks. For triangular numbers, verify that P3 when is n multiplied by n plus 1 over 2. We need to show this. So, since it's about triangular numbers, we consider r is 3, and using the general formula, it becomes P3 of n becomes 3 minus 2 multiplied by n squared minus 3 minus 4 n over 2. And it becomes n squared minus negative 1n plus n over 2. You can factor out n, and it becomes n times n plus 1 over 2 as required. The next 2 marks. The number 351 is a triangular number. Determine which one it is. So it is given that the value is 351 and we need n. So we can just equate E2, can use this, n squared plus n over 2, and we can see that we get a quadratic equation with respect to n, which can be easily solved. I will not do that. And there are 2 roots, one is negative, one is positive. Since n it's a number, it's positive integer. The answer is 26. So a number with number 26 has a value of 351. The next. 2 marks bi show that p3 of n plus p3 of n plus 1 is equal to, it means its identity, n plus 1 squared. So we need number with number n. So we use this general formula. It's n plus 1 over 2 plus number with number n plus 1. So it means we substitute n plus 1 for n. It becomes n plus 1, n plus 1 plus 1, so n plus 2 over 2 is equal to n plus 1, n plus n to n plus 2, and we can see that it's n plus 1 multiplied by n plus 1, so n plus 1 squared is required. The next 1 mark. State in words what the identity given in part bi shows for 2 consecutive triangular numbers. We need to explain this. The sum of 2 consecutive integers, or we can write that the sum of the values of the n's and n plus 1's triangular numbers is the n plus 1 n plus 1's squared number. The next 1 mark. For n is 4, sketch a diagram clearly showing your answer to part B I. So we need to show this result using some illustration. So and when n is 4, it means the 4th triangular number. So the 4th is 10, hence n plus 1, it means the 5th, and the 5th is 15. So according to this identity, 10 plus 15, the sum of values of 2 consecutive triangular numbers, is equal to the number of the greater number, which is 5 squared. It's 25, and we need to illustrate it. Since it's 5 squared, it's square, it may be not clear what do they mean, how to illustrate it, but it means the next. Since it's a square, 5 squared, so we can consider a square 5 by 5, and we need to show 10 plus 15, so we can use crosses for 15. So 15 we can do the next, do 15 crosses and 10 dots, so it becomes like this: 1 2 3 4 5 6 7 8 9 10 11 12 and 3 more. It looks like this. So you need to show like this. The next C, 3 marks, shows that 8p3 of n plus 1 is the square of an odd number, is the square of an odd number for all n is positive integer. It's a question. So let's consider again P3 of n. Formula is n plus 1 over 2, so it becomes 8 n plus 1 over 2 plus 1, which is 4n plus 1 plus 1, so it becomes even plus odd is odd. And we can see that it's true for any n is positive integer. The next, the nth pentagonal number can be represented by the arithmetic series P5 of n is 1 plus 4 plus 7 plus so on up to 3n minus 2. What does it mean? It means the first pentagonal number is 1, the second is 5, the third is 12, and so on. And question D, 3 marks, hence shows that P5 of n is n 3n minus 1 over 2 for n is positive integer. So some number with number n, it's the sum of terms of arithmetic sequence up to this term. So we can consider just a formula for the sum of the first n terms of the arithmetic sequence, and hence P5 of n is just the sum, and formula for the sum is u1 plus un over 2 times n, and it is equal to the first term it's 1, nth term it's just 3n minus 2 over 2 and multiplied by n because there are n terms in total. It's the first term, the second, and nth term is 3n minus 2. And when we just simplify it, we can see that it becomes 3n minus 2 plus 1. It's 3n minus 1 multiplied by n over 2 as required. The next question, 5 marks. By using a suitable table of values or otherwise determine the smallest positive integer greater than 1 that is both a triangular number and a pentagonal number. So let's use a calculator and we can set the next that it's as usual for functions. y1 it's for triangular, general formula is n plus 1 over 2, so 0.5 x squared plus x. And the second is pentagonal. Now for pentagonal numbers, the general formula is this, n 3n minus 1 over 2. And then just table, and we need the same y values or the same y value. Definitely it happens for different n values for triangular and for pentagonal numbers, and you need just consider this table, and if you consider, for example, let's consider up to 100, and we can see that there are no same value up to 100. Let's consider from 100 to 200. So you can see that there are no there is no the same value, and if you consider values from 200 to 300, you can see that there is the same value. It's 210. It's for n is 12 for pentagonal number, and it's also for triangular numbers when n is 20. So the first required number is 210. What is another way? Another way is the next. Since you need the same value, you can equate n plus 1 or n squared plus n over 2 and this value, but we should use another letter because it happens for different values of n. So let it be m, for example. So it becomes 3m squared minus m over 2, and we get the next quadratic equation with respect to n, and using discriminant we can write answer or roots as n is minus 1, in general plus or minus, but here it's definitely plus, square root 1 plus 4, 3m squared minus m over 2, and you need to consider integers for m, so that you get a number, so that a square root is an integer, and you can guess that it's for m is 12, and you get then that n is 20, and then substitute, for example, n or m, it doesn't matter, and calculate that the value is 210. And the next question, 8 marks. A polygonal number Pr of n can be represented by the series sum from 1 up to n, 1 plus m minus 1 multiplied by r minus 2, where r is positive integer and r is greater or equal than 3. Use mathematical induction to prove that Pr of n is this expression for n is positive integer. So we start as usual, consider the first possible value of n. Our proposition is this one, and we need that it's true, it coincides with this statement for any n. So for n is 1, we get the next. P r of 1 becomes r minus 2, 1 squared minus r minus 4 times 1 over 2, and we can see that it's r minus 2 minus r plus 4 over 2 is 1. which is true because for any polygonal number the first number is 1. So PR 1 is 1. It's true. So it's true for n is 1. The next step is as usual, we write assume true for n equals k. Assume true for n equals k, and we rewrite given proposition this, substituting k for n. So it becomes PR of k is r minus 2 k squared minus r minus 4 k over 2. And the next step is consider for n is k plus 1, we should consider PR over k plus 1, and our aim is to show that, and firstly we can just substitute k plus 1 for this proposition, so it becomes r minus 2 k plus 1 squared minus r minus 4 k plus 1 over 2, and we need to show that it's true, it's the same as sum from 1 to k plus 1 of this. And how to do that? Definitely, as usual, we should use this result. It will be needed. So we can open parentheses with k plus 1 and get the next. It becomes r minus 2 k squared, and let open parentheses, so it becomes k squared. So 2k times 1, 2k multiplied by r minus 2, and plus 1 multiplied 1 multiplied by r minus 2 minus r minus 4 times k and minus r minus 4, and we can see that this together with this, it's PROK, so it becomes PROK plus over 2 r minus 2 times 2k plus r minus 2 minus r plus 4, and let's simplify it. It becomes PROK plus 2kr minus 4k, r cancels, plus 2. We can divide each term by 2 and get PROK plus KR minus 2k plus 1. And what does it mean? PROK, it's sum up to k, and since we need PROK plus 1, it means sum up to k plus 1. And let's consider this statement, and this statement, if we consider sum up to k plus 1, it becomes sum up to k plus term corresponding to k plus 1, and we should substitute k plus 1 for m, so it becomes plus k plus 1 minus 1 r minus 2, and it's and 1 here, 1 plus 1, and we can see that it becomes sum up to k plus k multiplied by r minus 2k. So we must get this p, r, or k plus 1 to be true. And now let's compare with our result. So it's sum up to k, p, r, k. It's for sum for m from 1 to k over 1 plus 1 plus m minus 1 r minus 2 and plus 1 plus k r minus 2k, 1 plus kr minus 2k, and we can see that it's term corresponding to k plus 1, so finally it is equal to the sum from 1 to k plus 1, 1 plus m minus 1 r minus 2, and it's actually like definition of a polygonal number PR or n, and we can see that our proposition is true as required. So polygonal number of k plus 1 should be equal to this series, and we can see that it's true. So true for n equals k plus 1, and conclusion: if true for n equals k, true for n equals k plus 1. Since true for n equals 1, true for any n is positive integer. And that's all for this question.